So hi guys, I'm Michael. I'm going to be talking a little bit about Singularity containers, just a little background on me. I've been working with Greg on Singularity for about 1.5 years now. So let's begin. So first of all, what are containers, right? So on the right there's a logo, and we're just using that as a representation of a container image. What you do is you basically are making an encapsulation of your runtime environment. So you're going to take some operating systems, you're going to package them up into the container. On top of that, you're going to put some applications, libraries, configuration files, whatever dependencies you have. So in this example, you have some TensorFlow or Nginx or whatever. And then you have a self-contained and completely portable workflow that is just a single file. It's super easy to share, distribute. You can reproduce your results. You can validate your work. And it's all from a single file. So one important thing about Singularity is we sort of are differentiating ourselves from other container solutions out there, mainly via architecture and container format. So we'll talk about that in a minute and what that means. Is everyone here familiar with containers? Do we have a raise of a hand if anyone is confused about what a container is? All right, so maybe we just skip over this slide a little bit. Basically, we're just comparing the difference between a container and a virtual machine. Where on a virtual machine, you have virtualized hardware laying on top of the file system. Where in a container, you're just swapping out the file system and you're running applications as close to natively as you can. And again, just to reiterate, the difference between A and B is that C layer, which is the additional virtualization that comes with a virtual machine. So why Singularity? Why would we use Singularity instead of some other container technologies? Well, one, it's built specifically to support high-performance computing, scientific workflows, and as Greg writes up there, Singularity was built basically by demands from scientists, maybe threats, maybe bribes. Two, it's a single file container format. So when you have a single file, it's not some abstract concept of a container, it's just one file. You can move it around like you would move any other piece of data. You can encrypt it like you would another piece of data. And you can move it anywhere using, SCP, whatever you want. Again, this supports extreme mobility of your container. And because of this, because it's just another piece of data, by default it can sort of already be compliant with, controls compliant. Since it's just another piece of data, you can manage it, you can archive it the way that you would any other controlled data. And it's compatible. Because we've designed Singularity for HPC, you can insert it into any, complex HPC workflows that you want, and you don't have to do a lot of mangling and restructuring to get it to work. Because our security model is designed to support untrusted users running untrusted containers. Instead of in enterprise computing where you might have trusted users, root or some user that's been deputized by root, running a trusted container that's been signed and verified by, Nginx, for example. On HPC, we need to let any user run any container at any time for whatever reason, and we need to be able to trust that they can't do anything malicious. So up here we have a painting, and yeah, it's a good painting, but it's someone reproducing a Van Gogh painting. And without having access to, literally the identical source and, environment that original painting was created in, we can't create the exact copy of it. We can create something good, we can create something really good, but maybe not perfect. And the question is, what is close enough? What is the level that we need to be confident that our results are going to be reproduced? Is it 90%? Is it 95%? Is it 99%? Is it 100%? And here you can kind of see the difference, right? It's a good painting on the left, but obviously it's not the painting on the right. Anybody can see that. And so going back to the container model, it would be really great if what you could do with the painting is package it up into a container. And then now you can see that these are actually bit for bit identical copies of the same material. And so if this was instead a scientific workflow, you could be assured that the thing on the left is identical to the thing on the right, and no matter where you move it, it's going to remain exactly the same. And just to reiterate, the extreme mobility that's granted by having a single file container image, right? You can copy it on a parallel file system, you can SCP it, put it on a USB drive, and then that allows you to put it onto any resource, from Microsoft Azure, AWS, Penguin Computing, etc. So another sort of very differentiating feature of Singularity is our image format, this is new, this is coming in 3.0, which is slated for around January-ish, is the Singularity image format. So what's it going to support, right? First of all, cryptographic signatures and verification of the image itself, so you can, again, be guaranteed you're running the same thing. It's going to have faster access to sort of arbitrary container metadata that you might want to store with your container. You're going to be able to have multiple system partitions in the same image file, so you can support some complex images and complex workflows. And hopefully soon we're going to be having better support for checkpoint restore within the image so that you can checkpoint and restore. So this is what the new image will look like. It's similar to sort of the ELF format. We have a global header that describes the data. Then we have several different regions. We have maybe the recipe for the container, some labels, the environment variables, and then we have a system partition containing an immutable squash SVS file system that might contain, Ubuntu or whatever, or SUSE. And then on the end, we tag a signature block and we cryptographically sign each section of data. And so you can guarantee each section of data is exactly what you think it is and what it says it is. And so you say, okay, well, what if I want to change my container and I want to modify it? Well, at the back there, we actually insert another segment of data, which is instead of an immutable squashfs object, it's a writable overlay section. And so it actually, as it turns out, what you can do is you can make any amount of changes to your data. And so if for example, you're running a machine learning application and you're training a model, that's going to want to maybe write out some information about that model to the disk so you can later use the trained model. And instead of writing over the runtime environment, you're going to actually just write over the overlay, and it's going to basically be an evolving container, and the base of the container is still cryptographically verified. The only difference is that it has a non-cryptographically verified writable portion on the end. So just as a nice illustration, I really like this picture. It shows Singularity containers with a nice Singularity lock on it, so we can really lock down everything that's going on. So as far as systems compatibility go, I kind of already talked about this a bit. I said really the base security, the paradigm is we need untrusted users running untrusted containers. And to do that, we have to limit the security context of the user. So have to do things like make sure that the user running the container is the same user inside and outside the container. We need to use the kernel to make sure that we enforce certain security escalation preventions. We also need to allow users to access data that they own, but also not access data that they don't own. And so, traditional POSIX semantics apply in that regard. And so the configuration file is able lets a system administrator set some sort of rules or limitations. Can a user run only a specific image or a specific set of images? Can only a certain user run on Singularity? So we allow the administrator to really fine-grain the control that they have over who and does what, basically. And on top of that, we just want to make sure that we're always transparent and that we're open to working with the community. We want people to tell us if something is broken and something is insecure so that we can go and fix it as soon as possible, because we're not perfect, we're never going to be perfect. It just kind of happens. So as far as the architecture side, again, like I said earlier, we basically swap out the host file system, and so our contained processes are essentially running natively. We have just by default support for MPI jobs, support for jobs that run GPUs, and a very important point is that we have direct integration into resource managers. So if you're running, this is a traditional resource manager model. It calls the job on behalf of the user. It's a root execution daemon, and if you're using some container software that has a root daemon, you're going to actually reach outside that execution context, and you're going to have the daemon spawn a contained process for you, no longer in the context of the resource manager. For HPC, that's not very good. It requires a lot of workarounds. So what we do is, instead of going outside the context, we have no daemon. All we do is we sort of interject the Singularity process in between where the job would normally spawn the program. And it stays now fully within the context of the resource manager. And as it turns out, there's actually no Singularity process that hangs around. You run Singularity, Singularity sets up the environment, and it disappears, and your program is just running natively. And lastly, again, to talk about, it's a single file container image, which is actually very highly optimized for HPC systems, for parallel file systems. Can demonstrate that. So here's a graph in the red line is a person running a Python job across up to 1,000 nodes. And that Python instance is living on the parallel file system. And you can see the line go up. And then on the blue, that Python instance is instead living in a Singularity container. And you can see the time axis is logarithmic, so actually running default on the parallel file system is about 10 times slower than running in a Singularity container. Basically, that's because you only have to make one metadata operation per instance instead of making thousands of small file I/O requests, which will basically shut down your metadata server. How much more time do we have? A couple minutes? Okay. So just a quick intro to a couple commands. So, really quick, easy way to spawn up an interactive shell. You download Singularity, you do Singularity shell, and then you can give it any Docker image. So you do Docker : // in this case we have CentOS 7, and immediately you can see that you're inside of an interactive shell and you can play around and check things out. So I already talked about the shell command, and in this case we're using an image that already lives on the file system. There's an exec command, which lets you execute any command inside the container. So in this case, it's just listing some processes, but it can be whatever you want. It could be TensorFlow, for example. And then the run command is when you create a container, or when you create the container image, you can specify some script that is run when you do the run command. And when you do the run command, we're going to run the script that you specified earlier. And also, as it turns out, you can directly execute the image. You don't have to do the command, just execute the image and the script will run too. So here's just a nice pretty picture of a couple of our contributors. Thank you.
That's it. All right, let's give Michael a big hand. Michael, you win the prize. Let's give Michael a lightsaber for being a presenter in our booth. And also being the youngest presenter we've had by quite a bit, probably, here in our booth. How old are you?
20.
20, all right. He wasn't a teenager, that's good, so. All right. All right. Let's give away a couple backpacks. So, Michael, reach into the container there. Let's close your eyes, mix them around.
Is this a good one?
I think so.
There's a number on your chair for those of you that came late on the side. Don't take it off, but first, 12. Right back here. All right. Warren was there first.
Yeah.
First guy in the booth, so that's good. All right, let's try one more. One more. And
13.
13. 12 and 13. Nice. He gave it away to the University of Michigan friend there. All right. Well, thanks a lot. We'll be doing the next presentation here in the booth in 10 minutes with Intel. So please come back. If you're interested in that topic. So thanks again. If you have any questions for Michael, he's going to stay here for a few minutes with his lightsaber.